Hi, Professor and judges. My name is Yan Chen from Cranbrook Schools in Michigan. The topic of my study today is on applying a new integrated model, DNN with active learning, on a usually ignored field of application, engineering optimization. In my case, I'm going to focus on fluid dynamics. As is widely known, there are many mature and popular applications of artificial intelligence. For instance, virtual assistants we use, such as Google Assistants, involve the use of natural language processing. Bike sharing, object detection, and so on employ computer vision. However, the application in design optimization is for a long time overlooked. So, the key question we're going to ask today is, can machine design better? To explore this question, I will mainly discuss about research background, methodology, experiments, and possible future works in this presentation. To start with, why we focus on fluid dynamics? It is regarded as one of the most important factors of engineering design, for its wide applications and wide coverage of people under influence. Basically, on a large scale, such as designing a spaceship, into a smaller scale, such as biological injection into blood vessels, are all applications of the study. They all need to minimize their resistances with the study of fluid dynamics. And also for this reason, there are huge civil application potentials. So generally, everyone who drives a car, flies on a plane, or simply lives in a building with AC or turbines is under its influence. But the two key problems of the current designing process lay in its theory and application. The knowledge barrier is set by Navier-Stokes equation itself, which is the governing equation of fluid dynamics. It has its properties of complexity and insolvability. Because of its chaotic nature, even the understanding of the equation is challenging. In fact, it still remains one of the 6 hardest unsolved mathematical problems in the world, being awarded for $1 million for proof. Also, it has no closed-form solutions due to its chaotic nature. Therefore, for engineers to design, experts are involved in the process to first guess on the possible shapes and then prototype the results. Such process needs a lot of human domain knowledge and sets a natural barrier. The result produced by such estimation later moves on to be physically prototyped and tested, usually in a wind tunnel test. Such tests for physical property is a waste of both time, space, and resources. There are few previous works related to remedy the mentioned problems. Firstly, computer simulation. Now engineers can design based on simulation results from platforms such as MATLAB. However, the expert input is still unavailable and there is no way to make sure that the shape is actually optimized. Bayesian optimization done at Stanford University is the only study I found that is similar to our attempt to apply machine learning. However, their methods need too much data to train and still require some human domain knowledge to eliminate possible mistakes of prediction. Therefore, there are two key questions for our study to deal with. How can we make this design process even less computationally expensive with less human domain knowledge? Our solution is DNN over active learning. Now, let's look into methodology. I will include explanations for how we get the data, how we train DNN with active learning. Let's get started with MATLAB simulation. We use MATLAB to get all of our training and testing data. In order to make our algorithm more integrated, we use Python code to enable Jupyter Notebook to activate our MATLAB algorithms through creating two .tmp documents to record input and output data points, and using subprocess library to activate MATLAB. We use randomly generated 3D latent dimension lengths as our input of simulation. And each of our output data looks something like this, so these 3 graphs make up one of our simulated data point set. The entire process of simulation goes through 3D simulation and a projection from 3D to 2D. Then the algorithm produces a velocity map and a coordinating drag coefficient. Firstly, we use Navier-Stokes equation to produce 3D environment for the fluid dynamics system. The equation includes all of our listed variables in the legend section, which stands for each element of a fluid environment. As is shown in the 2D demo, the way we make our simulation is to fit BSP lines based on 3D dimensional lengths. Smooth curves are drawn around those dimensions to create an object. Then we map the 3D shape into 2D. We achieve this process by creating a geometry that represents the object in its relevant boundary conditions. Then we create a mesh to represent the state of each point of the system. We use a MATLAB add-on called QuickSim to fulfill this conversion. At the same time, we convert the mesh condition map into a color-coded map that represents the relative velocity of each point. Those velocities are shown by the color bar on the right side of the graph, such that the relative velocity of the environment in contrast to the object is revealed. Finally, we apply this equation to calculate the drag coefficient of the object, given the information provided at the time of simulation. For this specific case, the drag coefficient is calculated to be 0.41408. The second thing we need to do is to fit a trend to predict resistance. To do so, we use the deep neural network because of its flexible function family and ability to capture hidden relationships between each input. Specifically, we have the fully connected layers denoted by the equation at the top, with W being weight, X being our input, and B being bias. W and B will be our training parameters. We use value as our activation function. For selecting specific methods of training, we compare the performance of different models. Here, we take CNN and DNN for examples. Because we have quite characteristic traits for our velocity graphs, as different colors stand for different velocity, which is a substantial factor of the drag coefficient. This may naturally lead us to think about using CNN because of its popular method. It's a popular method that model regression directly from 2D images. However, although this method deals with the reduction of human domain knowledge, we will still need to simulate a huge amount of data and train with more computation costs because of its two-dimensional nature. The sample size would exceed hundreds of thousands, in fact. That's why we choose to use DNN, which will avoid such a computation burden with its numerical input. To extract such numerical inputs, we create latent dimensions on the 2D object by dividing them into 8 pieces. Then take 4 of its representative dimensional lengths as our input number array. These 4-dimensional arrays become our training input to build a deep neural network architecture as this. We have compared architectures of different layers and different neuron numbers of each layer. This architecture optimizes the regression performance. Each layer is connected through the fully connected equations is represented on the bottom right. Each input dimensional data is convoluted by 5 layers of weights and biases, which are trained variously to achieve optimal performance. Third, and also the last thing we will include in our study is active learning. This is used to further reduce the number of data points needed. Its ideology is originally to input limited amount of data and have machine raised unlabeled data points for further information provided by human experts. However, in our case, we realized that our model would raise only predictable decisions for humans to make, so we designed 2 loops to avoid human inputs in this process. The first cycle is to ensure the model is being trained optimally without human input in adjust parameters such as training steps and epoch. We have machine enumerate through all possible parameters on their own discretion. For example, the only possible range of the training step is from 10 to the negative 1 to 10 to the negative 5, so this only has to enumerate 5 times as a maximum. This ensures that our model finds the least possible mean square error prediction. The second cycle judges if our model is going to retrain itself. This happens when our fitting does not find the optimized shape. This judgment is done simply by comparing the predicted optimal case with previously existing data points. One thing worth mentioning is that in order that our model does not miss the most optimized shape, the model will retrain itself for one more round even if the predicted case is smaller than all the previously existing cases. This active learning process can be visualized by this demo. For the purpose of visualizing it, we ignore 2 of the 4 representative dimensions and only leave width and height. Then we project the drag value onto the z-axis. As we can see from the graph, The optimal shape predicted by the plane fits the trend in the first round of training shows a shape that is not all that optimal. Of course, this is captured by our mechanism so that the newly produced shape is included into the training dataset and have our model retrain itself. Such process will continue until optimal shape, as shown on the top right, is secured. Now, let's look into how our model does its job. So, as I mentioned in the previous sections, we produce only 625 samples for the training purpose compared to 8,000-ish for a similar work. We also apply tenfold validation methods so that we have the divisions of our training data points as such. This graph shows the convergence condition of a model. These two graphs shows an example of how our active learning algorithm performs. The one on top is the result of the first training. As is seen, it is not yet optimized. And the one on the bottom is the final result, from which we get a sense of streamlined structure. Compared to a similar work done by a group of Stanford researchers, our model reduces the computation cost, as is shown by the significant reduction of computation time. Largely due to our use of DNN with active learning, the time we use to produce all needed samples is 4.5 hours, 72% less than their study. And because of the use of number array as input for deep neural network, it only takes us 5 minutes to train the model, which is a time length 92% less than theirs. Compared with traditional regression models, on the other hand, the largest margin shows a 75% smaller testing MSE value, while the smallest margin still shows a 16% deduction in training MSE value. Finally, to sum things up, let's look at the entire pipeline for review. So first of all, we use MATLAB for simulation, where we simulate a 3D system and map it into 2D. Then we correlate shapes with according fluid resistance. Then we train our data with deep neural network, which avoids human input. Finally, we apply active learning to reduce the computation cost and ensure our prediction. To put it in a nutshell, our system finds a creative application of artificial intelligence on further mechanics optimization. In this process, we also self-designed a way to simulate and collect the data, which has a structure that helps us reduce computation burden and computation time. We also contribute to the use of algorithm, as we successfully combine the use of deep neural network with active learning. All these together form our optimization system. For sure, there are also some future works for extension. We use pure water situations with viscosity of 0.2 to make our study more general to all fluid mechanics. More specific conditions may be simulated in the future. For some conditions that are too complex for simulation, we may also utilize the data from previously tested wind tunnel test, so that no further prototyping is needed. Also in the future study, we may look into other characteristics of engineering design, such as agility of cars and planes, and so on. Moreover, the use of our model, active learning over deep neural network, may find applications in other fields as well. And our method to reduce the dimension of graphs before training can be used for reducing computation expense in other works too. And here are a few pages of reference and bibliography. Finally, I'm really thankful for the invaluable opportunities Google Science Fair makes available, including and especially for having this research paper viewed by a committee of expert judges.